Okay, section 3.4, three-dimensional wave propagation. We have seen it the simplified version of 1D wave propagation in a bar. We have seen it for a P wave, or the hammering stress we applied on the bar, or a torsional wave, the twisting moments we applied on a bar. That was for 1D case. Now let's see how it looks like for 3D case. Just to inform you on the outcome, surprisingly, they are identical. Whatever you do, 1D or 3D, the wave solutions, finally, they will give us the same shear wave velocity and P wave velocity. It's not different between 1D and 3D. But we'll quickly go through the 3D steps, how it is obtained, and see the final wave velocity equations. And that's what this section is. 3.4 is the 3D version of the 1D we just discussed. So for 3D element, if you remember from our stress-strain relations, if you take out a 3D element from inside the Earth, let's say it has a dx, dy, and dz dimensions. And you have also, let's say, now stresses, because some dynamics is happening on it. In the case of static, it was in equilibrium. Now, in the case of dynamic, it's also in the dynamic equilibrium, but you have a stress applied from one side, and you have some change of stress. The sigma x on this side is now sigma x plus delta x. You have some change of stress. Don't worry right now about whether it increases or decreases. If we apply it on this side, most probably when it reaches the other side, it decreases because of damping and everything. And sometimes it can get amplified, depending on the soil properties and some characteristic. But that amplification, de-amplification, we'll discuss it later, the cases that cause that. But for now, sigma s on one face, on the left face, this is the face I'm considering. And on the right face, if you see this, the YZ plane, it would be sigma x plus a rate of sigma x with delta x times the dx, which is a dimension of that element along x-axis. So you have the same with the shear stresses on the faces, same change, and in all directions, in all 6 faces. So now for this element, this solid element, to be in equilibrium, let's say there is a dynamic wave passing through here. So call it a stress wave passing from one end to the other end. If this element is in a dynamic equilibrium, then the sum of forces from Newton's second law should be mass times acceleration. So let's consider it in the x direction. In the x direction, look at it. You have sigma x, changing sigma x along the x-axis, which is this face, minus on the other face, which is sigma s. And this is stress. So to change it into a force, you just multiply by the dimensions or the area. This area is dy times dz. Sorry on that. I had one of my kids' iPad Viber dialing. So if you see, same is true for the shear stresses. Shear stress in the Zx, the change, minus the shear stress times that area. Shear stress in the Yx, do the same thing. So these forces, the normal stress and the two shear stress on the face, we're considering the forces acting in the x direction, equals to mass times acceleration. The mass is density times, this is a volume, times the acceleration. where density is just the medium density and U is the deformation in the X direction. If you do this force equilibrium in the X direction, then and simplify the equation, you will arrive to this equation. Second degree partial differential equation in the form of normal stress and shear stresses and the acceleration. You can do the same exercise, the same algebra for the Y and Z directions. Stress in the Y and stress in the Z direction. Same equilibrium. We did it for X, do it the Y and the vertical Z direction. You will arrive to these equations, where V is the displacement in the Y direction, W is in the Z direction. Now, this is the form of the equation we have for X direction. Stress in the X direction and those shear stresses. And if we substitute these equivalences for shear stresses, we say shear stress in the XY equals shear stress Y in the YX direction. For equilibrium, they have to be the same. Or X is equal to ZX. Then what you'll get, you substitute here. This is stress at different planes. But if you substitute this equivalency, then what you get is stress on the plane perpendicular to x-axis. U is the deformation, stress in the X, sigma XY, XZ. So these are forces on the x-axis plane. And we know that from Hooke's law or from our stress-strain relation, shear stress is G times shear strain, XY, you can also XZ direction. And the normal stress also, we have this in the form of the volumetric strain and strain in the X direction. We reviewed these equations. Now substitute these equations. So this stress sigma X is here. Now put it back here. This is sigma X. And shear stress XY, put it in the form of shear modulus and strain. Shear modulus and strain for the Z direction also. For the shear stress XZ. And normal and shear strains, we have this relation from our review of stress relation. Normal stress, normal strain, deformation in the X direction by the length in the X direction. The shear strain in the XY, shear strain in the ZX. So these are what we have from engineering mechanics. We reviewed them, I think, section 3.2. Now let's put back, replace all this. You see shear strain here, replace them. And strain here, replace it. We're trying to simplify the whole equation. Replace those. This is what you see. They are replaced. And simplify the equation further. And group them. And epsilon bar is volumetric strain. This is what it is. So this all you see is a volumetric strain. And the change in volumetric strain along the x-axis, now this is the change, which is the first derivative. You can do the derivative with respect to x, partial derivative, and this is what you get. Do this. This is what your volumetric strain. Do additional derivative with respect to x. This is what you end up. Now, this sounds familiar right here. Then substitute it. We did here. And this is still remains. This is more algebra. You can follow it, the steps. It's more algebra. So we have this equation final. Now, if you further simplify it, what it gives you is you can reduce the partial differential equations for the wave in this form. This is a second order derivative equation. Lambda plus G, volume, this is volumetric strain, shear modulus, and the Laplacian operator. And U, the deformation in the X direction. The Laplacian operator is represented by here. This is for, we did it for X direction, but you can repeat the same exercise for Y and Z directions. And you'll find the same in the Y direction. Remember, V is the displacement in the Y direction. W is in the Z direction. So you can find the similar equations. So this is the equations where we finally obtained. The stress wave equations, the second order equations, they have this form in 3D. In the X direction, in the Y direction, in the Z direction. If these are the wave equations in 3D, this is a more practical case. In reality, the wave travels in any direction. So this is what you can get. Now, what is the solution for this wave? Let's see the solution to compressional wave velocity. Compressional wave particle motion is along the axis of the wave. Let's say x-axis. Solution to the compressional wave velocity can be obtained differentiating each equation with respect to WRT is with respect to their own axis. The x, because the wave is traveling in the same direction, now you can differentiate this with respect to x, with respect to y, with respect to z. And adding them together. Differentiate them with respect to their axis and add them together. If you do that, look at it here. This is what you find. This is a common term. The first equation, you differentiate with respect to x. The second, the v with respect to y. The w with respect to z. We are interested in the p wave. The p wave travels in the same axis. That's why that differentiating it. And the same thing, do that differentiation on the other side and add it. This is what you end up. You can follow this in your time. Now, the final equations you end up will have a condensed form of this, or this one. You have the Laplacian operator, the VP square, volumetric strain. It's a second order differential equation. That VP, because the VP, we represent it as a VP, but it's actually, it's obtained from these parameters. So that VP is actually what you have right here. Whenever I put this in red borders, what I meant is that's what you need. Whatever operation we did on the wave partial differential equations, our final product is the VP, the primary wave velocity for a 3D case is lambda plus 2g over density. Lambda is just the Lame's constant. Elastic modulus, it's a function of elastic modulus and Poisson ratio. G is the shear modulus. We know that shear modulus is elastic modulus by 2 times 1 plus a Poisson ratio. If you put this together, replace lambda here and G here, you end up VP is this much. Remember, this VP is very identical to the one we get from the bar, which is a 1D case with a constraint modulus. This is the constraint modulus, M. We call it M. Why is it same as the case of constraint modulus? Because our element, remember, the element we took is from deep inside the Earth. This is the element we worked on. We have stress in all directions. We are assuming this is the general case. It's constrained from every direction. There is no free surface here without stress or forces. It's constrained from every direction. So a solid element actually taken from deep inside the Earth is as if it's constrained. That's why you get that VP is identical to the constraint modulus, M. Epsilon bar is a volumetric strain and VP is a velocity of dilatational wave. Dilatational wave is same as primary wave P wave or compressional wave, because we assume the wave is propagating in the same direction to the axis. Note that the compressional wave velocity, P wave, in elastic 3D medium is identical to the one with solid bar 1D case with constrained condition. That's the main conclusion. Whether you do a 1D case or 3D case, for primary wave, you have identical solution. Let's see the solution to a torsional case in case of the 3D element, which means that the 3D element is being twisted, it's being rotated. Let's say it's being rotated about x-axis. This is our relation from stress-stress relation that we just, stress-strain relation we just reviewed in section 3.2, I believe. We can apply derivation on this stress-strain relation and get, which means it's a twisting case. And we can differentiate it with respect to the other axes. We don't differentiate now with the same axis. If you differentiate with the same axis, it's a P wave. But if you differentiate the orthogonal axes, now it's a S wave. The wave is propagating the x-axis, but do the differentiation in the orthogonal axes, because that's how the particle movement is. Or you can see it here also in the rotational equation, stress-strain relation. We're doing rotation about x-axis, but the differentiation is about y-axis and z-axis, because we are more interested in the orthogonal directions for a shear wave, or it's also called a torsional wave. So differentiate the wave equations. Now these are the same wave equations. Whether it's a P wave or S wave, it's the same. But now do the differentiation with respect to the opposite axis. Differentiate with respect to y-axis, and differentiate the wave equation about z-axis, and you'll end up with these forms. Do more algebra, and subtracting the resulting equation provide, now you have the reduced with the Laplacian operator. And finally, your final product is the wave equation now comes in terms of rotation. It's a second order partial differential equation, but look at what it's providing. The Vs square root of G by rho. This should be familiar to you. It's identical to the 1D case, the bar case, where we apply twisting moment on it, a dynamic moment. So the equation forms, whether it's a primary wave, a shear wave, torsional wave, they're identical. What's different is the way the distortion in the element. In the primary wave, it's compression, dilatation. In the torsional case, it's twisting. The element is being twisted. It's rotating. That's why you have this term. Instead of, for the primary wave, we have it U. Now we have it rotation. For that rotation, now it's the shear wave velocity. So the conclusion is a torsional wave velocity, S wave velocity, we call it shear wave velocity. The stress that occurs from a torsion is identical to the shear wave. That's why we alternatively call it. In elastic medium is identical to the solid bar. Whether you use a 3D element from deep inside the earth or a 1D bar, the final product is the same. So that's our interest. We went through this exercise, went through your advanced math, engineering mechanics, stress-strain relation, and finally what we obtained is the shear wave velocity and the P wave velocity. So now what it means is, let's say you have Earth, you have an earthquake occurring, and that wave is propagating something like here. It's in a curve. Why it's in a curve? I'll show you. It's not going to be like a straight line. You may have a straight line, but because of stratification, waves bend when they hit different velocity, different materials. Because different materials, they have different wave velocity. You can see it here. Different soil have different G and different density. So the wave velocity change. And when waves travel, they bend away or towards the normal. So usually you have some curvature to show that. So our interest is, this is the epicenter where it's occurring, a focal point. And now we know how much fast it is traveling. The Vs and Vp. So that's the takeaway. So all this, differential equations we looked at, it's trying to get the Vs and Vp. And the Vs and Vp, fortunately, they are as simple as this. If you know the shear modulus of your soil from a lab test and the density of the soil from a lab test, you can tell what speed the shear wave velocity is going to have in that soil. This is applicable equally to anything. It can be metal, it can be concrete, it can be soil, anything. But the shear wave velocity in that medium is expressed as simple as g square root of g by rho. The same is true for a VP, except now you'll use elastic modulus or constraint modulus depending on the state. That was for one direction, I believe. We did it for X direction. You can do the same with the Y and Z direction. And you'll end up with the same thing, except rotation is now about those axes. But the final product is the same. Shear wave velocity is square root of g by rho. G with the shear modulus is elastic modulus by 2, 1 plus mu. And a shear wave velocity, you can also express it, in terms of elastic modulus. So let's summarize whatever we have seen so far. We went into a lot of advanced math, derivations, after looking at the wave characteristics and stress-strain relation. Here is our big takeaway. Based on the velocities of compression waves and shear waves as derived in the preceding section, the following general observation can be made. Number one, there are two types of stress wave that can propagate through an infinite elastic medium. Why we call it infinite? Because we are talking body waves. That's why. Infinite medium, we are assuming it's extended very large on the other side. We are deep inside the Earth. If we are on the surface of the Earth, that's another one. That's the surface waves. But what we did, the solid element example we did, it's deep in it's constrained. It's way deeper in the Earth. That's why we call it, it's an infinite medium. It's infinity, assuming that the Earth is big, the element we took here is big, so infinite in every direction. The other option is half a space. We'll come to it. If you stand at the top surface, you have only half a space below. It's half. You don't have the other portion at the top. And we call it elastic because we are assuming the waves to propagate elastically in that linear range. We're not considering the plastic deformations. When earthquake occur, so many things happen. You have a heat loss, friction loss, sound loss, and also some faults can occur, right? Cracks occur everywhere. The cracks are plastic deformation. We're not looking into that. If you see the majority propagation of the wave is elastic. Around the surface, you may have cracks occurring. So that plastic deformation, we're not looking into it. It's a linear range. So these two waves, and they travel at different velocities. One is the primary wave, one is the shear wave. We know that the primary wave, we have this equation for it with the constraint modulus. And the shear wave, we have this form, g by rho, square root of g by rho, shear modulus by density, or you can represent by this. Now look at this. Let's see the ratio of the primary wave by the ratio of the shear wave velocity. It's the square root of, just do this algebra. This guy right here divided by this. E will cancel out, density will cancel out. What you have is just an equation in the form of Poisson ratio. So now this has something. This ratio for our materials, common materials, this ratio is always greater than 1. Which means you can have 2 here, 1 minus mu divided by 1 minus 2 mu is always greater than 1 because you are reducing more here, right? So this thing is larger. What does it tell you? It's telling us Vp is greater than Vs. If this whole thing is greater than 1, then it's telling us Vp is greater than Vs. This is true science. This is true mathematical derivations. Through recording also, we know that the first wave to arrive is the Vp. After the Vp, after a few seconds, we record also the shear waves. So this is a mathematical proof to what our recording shows. Second, the more rigid the material, high G or high E, high shear modulus, or high elastic modulus, you can see it here. If you have high E or high G, the higher the shear and compressional wave velocities. If it has high rigidity, then the P wave and the shear wave are much higher. Shear and compressional wave decrease as density materials increase. Density of materials increase. So look at the equations. If somebody, by common sense, we may say, oh, the denser the material, the higher the shear wave velocity. No, that's not true. Density is inversely proportional to velocity, shear wave velocities. If something is very dense without being rigid, shear wave velocity is very low. Now, the other conclusion. Liquids, example, water, does not have rigidity, or G is very small, near to 0. Shear modulus is 0. Hence, shear waves cannot propagate through liquids. You can prove that right here. If you put G near to 0, the shear wave velocity is 0. Shear waves do not propagate through liquids. We made that conclusion in chapter 1, in the introduction section. But this is the mathematical proof. Shear waves do not propagate through liquids and gases because there is no shear stiffness there. That conclusion also helped us, to determine the inside of the Earth. Remember what we said, the shadow zones? If an earthquake occurs, then you have a shadow zone where if this is a shear wave, this entire area is not experiencing the shear waves because the core, the outer core is liquid. No wave is passing through it. No shear wave is passing through it. So any recording station in the world which is located in this area is not going to experience shear waves because the outer core is not allowing it to pass. So this concept helped scientists in the past to make judgment on the content of the interior of the Earth. Sorry on that one, I had another call. And another conclusion, as Poisson ratio is close to 0.5, the velocity of compressional wave becomes unbounded. You can see it in the equation. All these conclusions are based on the equations. Compressional wave, this. As mu is close to 0.5, this is going to 1 minus 2 times 0.5. This is going to be 0. So this guy is going to infinity. That's what I mean unbounded. So numerically, you'll have that error. Any software like FLAC, Plaxis, or SASI, any geotechnical software, if you put Poisson ratio of 0.5, you'll get a numerical error. So usually what we do is we limit it 0.4849. And that's even for a saturated case, because water is close to 0.5. Soil is normally below that. Soil is 0.3, 0.35, 0.4. But when you have a saturated soil, because of water, it can get close to 0.5. So in the softwares, when you put the mu, you have to be very careful. If somebody tell you for a saturated soil, you use mu is equal to 0.5, then that solution is, if you do a dynamic, seismic simulation, it's going to explode. It's going to show you a lot of error. You may not realize some softwares give you heads up. Hey, you cannot put 0.5 for mu. They have a limitation in their manuals because of this, because the waves are going to explode. Compressional waves are faster than shear waves. We know that from recording station. We have seen it in chapter 1, but there is also a mathematical proof. This comparison VP versus VS is showing us for any material you put here. So like if you put mu is equal to 0.3, you're going to get VP greater than VS. When an earthquake occurs, compressional waves arrive first to a recording station, followed by shear waves. So this is the big takeaway I want you to understand. If you're interested, you can go to the detailed math we discussed. It gives you mental, satisfaction. But the big takeaway is how the waves behave. What's the final equations for the wave velocities? That's what we are more interested. The last conclusion we had, these compressional waves are faster than shear waves. You can see it in a plot here. VP by VS. If you have different Poisson ratios, 0.1, 0.2, 0.3, 0.4, 0.5, this is what you get. If you reach to 0.5, that's what the infinity case happen. So you have to be careful. But other cases, you have everything above 1. You see it here. 1 is right here. So for any Poisson ratio, the VP by VS plot, it shows you it's more than 1, telling us the primary wave velocity is larger than the shear wave velocity. That's exactly what we record. You can see it on the plot on the right side. When an earthquake occurs, this is a sample from a recording station. First, we see first P wave. Give us a little bit because the P wave arrives first. Then the S waves arrive. Then the surface. When the P and S wave, these are the body waves. When the body waves hit the surface, then the surface we start observing the Rayleigh and the lava waves, the undulations on the ground. And these ones are those. P is faster than S wave and arrive first at the recording station. So it's more, they are going together. What we record in the field is matching what the mathematicians developed for the wave velocities. Table below gives some typical values of VP and VS encountered through various types of soil and rock. These are just sample examples. For example, a fine sand layer can have a wave velocity around 300 meters per second, primary wave, and a shear wave from 90 to 150. This range is given because of different shear modulus, different densities you can have. But C, the value is less than the P wave. Dense sand can have 460 P wave, around 230 VS. Gravels, 762 VP, and VS is around from 108 to 50. Moist clay. Now, moist clay, we're talking about saturation condition. The P wave is much larger. When you have water, that mu is getting close and the P wave is much larger compared to the S wave, see it. For the others, the ratio was small, maybe twice like that. But when you have water in it, saturation, it gets too large. Granite, now we are reaching to the rock zone. Rock hard, much larger. Because of the elastic modulus or the shear modulus are much higher, so you have higher velocities for P wave and S wave. So try to have a feel of what different kind of soil have different kind of shear wave and P wave velocities. Normally, as you go deeper into the surface of the Earth. If this is the ground, let's say, if you go deeper, rigidity or elastic modulus increases. Density also increases, but the increase in rigidity and elastic modulus is higher, then Vs and Vp gets much higher. You can see it here. Usually at the shallow surface, you have loose soils, fine sand, maybe it's 300. And at some point, you may hit a bedrock. See, that bedrock can be granite or sandstone. See how much you have. So we will see how we determine the wave velocities. We have a lab test also. If we don't know the shear modulus, if you don't know the densities, there is a lab test we can do to determine wave velocities. And also there is a lab test, there is also a field test, a wave propagation test. If we don't know the soil properties. If you know the soil properties, it's easy. We can use the previous equations. If you don't know, there is a lab test, field tests we can use. But we'll see that detail in chapter 5. This may be a good point to stop the class, and we'll continue next Monday.